Welcome back, deep divers. Today, we're going to tackle something that's all around us, but most of us probably don't think about too much. Electric current.
It's one of those things, we use it every single day,
Every day.
but really understanding it.
It's kind of mysterious. So we're going to do a deep dive, obviously. We've got this physics textbook chapter here.
Yeah, this is a great one. left103.pdf. It really breaks it all down.
It does. And thankfully I've got you here to help me break it all down.
Happy to help.
So I was reading through this, getting ready, and I'm like, whoa, we're going to be talking about stuff like how currents actually work at like the atomic level.
Oh, yeah.
And then even like how our devices are powered. That's crazy.
Yeah, and what's really cool is we're going to find out what makes those little electrons drift and how fast they actually move.
Yeah, I'm kind of curious about that. So I guess first things first, what exactly is electric current?
Well, the textbook, it defines electric current as the flow of electric charges.
Okay.
But like to really get it, visualize it, think of a river. Think of how the water flows. The water molecules, those are kind of like our charges.
Okay.
And the more water that's flowing past a certain point at a certain time,
Yeah.
that means you've got a stronger current.
So it's the amount of flow, not necessarily the speed.
That's a great way to put it, yeah.
Okay. So instead of water molecules, with electric current, we're talking about tiny little electrons
Exactly.
zipping through wires.
Exactly, zipping through wires. And in most of our conductors, especially in metals, it's those electrons that are the charge carriers.
Okay, so it's the same idea, just at a much smaller scale.
Right, just like that river analogy, a stronger electrical current just means that more electrons are flowing past a point each second.
Okay, I'm with you. Now, the textbook mentions steady and non-steady currents. What's the difference between those?
All right, so think of it like this. A steady current, that's like your river flowing smoothly. You've got a nice consistent amount of water going by. But a non-steady current, that's more like a flash flood.
Ooh, yeah.
Yeah, a sudden surge. So if we think about it in terms of electricity, something like your household appliances, they use a steady current, but then something like a lightning strike. That's a dramatic example of a non-steady current.
Okay, yeah. So one is consistent and the other is who knows what's going to happen.
Exactly.
Right, so we've got these electrons flowing. But how do we actually measure how much is flowing?
Good question. So we use a unit called the ampere.
Okay.
Or amp for short. Most people just say amp. And basically, 1 amp means that you have 1 coulomb of charge flowing past a point every second.
Coulombs. I remember that from our electrostatics deep dive. It's all coming back to me now.
Exactly. Everything's connected.
But to put it into perspective, how many amps are we talking about in, say, our everyday devices?
Okay, so your typical household appliance, you're probably looking at a few amps. But then on the other end of the spectrum, a lightning strike. That can carry tens of thousands of amps.
Oh, wow. Okay.
Yeah, crazy.
Yeah.
But then on the other end, you've got the electrical signals in your nerves. Those are measured in microamps.
Whoa, so tiny.
Millionths of an amp.
That's wild. It's just this massive range.
Huge range.
So we've got these electrons flowing, but what actually makes them start flowing in the first place?
All right, so this is where electric fields come into play. Remember that example from the textbook with the charged cylinder?
I think so.
Yeah, so basically you've got this difference in charge, and that creates an electric field. And that field, it acts on the charged particles and makes them move.
Okay, so in that cylinder example, the electric field is what was kind of nudging those electrons to try and even out the charges at either end.
You got it. That's exactly it.
Okay, and that movement of electrons is the electric current.
Yes, that's the current. But here's the thing. To keep it going, you need a continuous source of that electric field.
I see. So it's not a one-time push. It's got to be continuous.
Right, and that's where your batteries and your power outlets come in.
They're providing the ongoing push.
They provide the push. They keep those electrons moving.
Okay. So now the textbook talks about this thing called Ohm's law.
Oh, yeah.
Which seems to be a pretty important relationship between voltage, current, and resistance.
It is. It's fundamental. So Ohm's law, it basically states that the current flowing through a conductor is directly proportional to the voltage across it.
Okay.
But there's another factor, and that's resistance.
Right. The equation is VIR. So V is voltage, I is current, and R is resistance. So resistance is basically how much a material, fights back against the flow of current.
That's a great way to put it, yeah.
Okay, so it's like friction.
Kinda, yeah. And this resistance, it depends on the type of material A and G, its size and shape.
Oh, interesting. So different materials have different resistances.
Absolutely, yeah. And even the shape matters. Think about it, a long, thin wire, that's going to have more resistance than a short, thick one, even if they're made of the same material.
Okay, yeah, that makes sense. Like trying to force water through a tiny, narrow pipe versus a big, wide one. The narrow one's going to resist the flow more.
Exactly, you got it. And that's why, you see thicker wires used for appliances that need more power.
Oh, right, because they can handle more current.
Exactly. They can handle higher currents without, overheating or causing problems.
Mhm.
Now, the textbook also talks about something called resistivity and conductivity, which are properties of the material itself.
Oh, right. So it's not just about the shape, it's about what it's made of, too.
That's exactly right.
Now, this is where it starts to get really interesting for me. The textbook goes into this whole microscopic world of how the electrons are actually moving. And it talks about something called drift velocity.
Ah, yeah. Drift velocity. So it's basically the average speed of electrons as they move through a conductor. But here's the thing. They're not just moving in a straight line. It's not a straight shot. They're constantly bouncing off the atoms of the material. It's kind of chaotic.
Oh, wow. So it's this kind of like zigzaggy path.
Exactly, yeah. And it's this net movement, despite all those collisions, that's what makes up the current.
That makes sense. I'm picturing like a crowded room and those electrons are like bumping into people as they're trying to get across.
Perfect analogy.
Okay, but wouldn't that mean then that a thicker wire, while it gives less resistance, it also means more electrons, so potentially more of those collisions? How does that balance out?
You're exactly right. A thicker wire does have more electrons, but it also provides a wider path for them to travel, which reduces that overall resistance. It's kind of like having more lanes on a highway.
Ah, I see. So more cars can travel smoothly, even if there's more traffic overall.
You got it.
Okay, that makes sense. Now, the textbook was saying that this drift velocity is actually super slow. Like example 3.1 even calculated it to be just a few millimeters per second.
Yeah, it is pretty slow.
But wait a minute, millimeters per second? But then how does like a light bulb turn on instantly when I flip the switch?
Ah, that's a great question. It's because the electric field itself, it spreads through the wire at nearly the speed of light.
Oh, okay, so the signal to get them moving is super fast.
Yeah, it's almost instantaneous.
Even if the electrons themselves are taking their sweet time getting down the wire.
It's like a chain reaction. You flip the switch, the field gets set in motion, and then boom, all those electrons start moving almost at the same time.
That's amazing. So it's not that the electrons are traveling super fast from the switch to the light bulb.
Good.
It's that the signal to get them moving is almost instant.
Exactly. It's kind of mind-blowing when you think about it.
It is. So is Ohm's law, is that like the be-all, end-all of electricity? Does it always apply?
Well, Ohm's law is a fantastic starting point,
Okay.
but it's not the whole story. It doesn't apply to everything.
Right, because the textbook did mention that there are situations where Ohm's law kind of breaks down.
It does, yeah.
What are some examples of that?
Well, think about something like the filament in a light bulb.
Oh.
As that filament heats up, its resistance actually increases.
Oh.
So the relationship between the voltage and the current, it becomes nonlinear.
Ah, so it's not that simple, straightforward relationship that we see in the equation.
Right, exactly. And these, we call them non-ohmic devices.
Okay.
They're incredibly important in electronics. For example, diodes, diodes.
Yeah, I've heard of them.
So those only allow current to flow in one direction,
Right.
which is super important in all sorts of circuits.
So it's cool how these little deviations from Ohm's law actually open up a whole new set of possibilities.
Absolutely. It's all about understanding the nuances.
Now, speaking of changing resistance, how does temperature affect all this? I know we talked about it a little bit earlier.
Yeah, so temperature plays a big role in resistivity. For most metals, as the temperature increases, the resistivity goes up too.
So it's harder for those electrons to flow when it's hotter.
Exactly. Think about it like that crowded room again.
Okay, yeah.
It gets more and more chaotic as the temperature rises.
Yeah, like everyone's bumping around more.
So it's harder for those electrons to get through. But now, here's where it gets interesting. Semiconductors, they actually behave differently.
Oh, really?
Yeah. Their resistivity decreases as the temperature increases.
Wait, so they get better at conducting electricity when it's hotter?
You got
That's the opposite of what I would have thought?
Yeah, it's counterintuitive. But a great example of this is the nichrome heating element in a toaster.
Ah,
Okay, so nichrome is an alloy, and it has a resistivity that stays pretty stable, even at high temperatures.
okay, so it can get really hot without changing too much, which is perfect for making toast?
Exactly. It's perfectly designed for that purpose.
Okay, so we've talked about how electricity flows and all the different factors that affect it.
Yeah.
But now I'm kind of curious, where does that electrical energy actually come from in the first place?
Okay, so that's where we get into electrochemical cells, or as most people know them, batteries.
Okay.
And these are sources of what we call electromotive force,
Yeah.
or EMF for short.
Right, EMF. I remember that from the textbook. There's even a diagram that explains how batteries work. But I'll be honest, I'm always a little fuzzy on what EMF actually is.
So think of EMF as the potential energy difference that a battery provides when it's not connected to a circuit. It's like
Hmm.
it has this potential energy ready to go. It's like a pump,
Okay.
that's ready to push charges through a circuit, but it's not actually doing anything yet.
Okay, so it's not a force in the traditional sense.
Right.
It's more like potential energy just waiting to be unleashed.
Exactly. That's a great way to put it.
Okay, I like that analogy. But like any real-world pump, I'm guessing a battery isn't perfect.
You're right, it's not perfect. And that's where internal resistance comes in.
Ah, okay.
It basically represents the energy that's lost within the battery itself.
Makes sense. Now, things can get kind of complicated when we start connecting multiple batteries and resistors together and we start creating a circuit.
Yeah.
How do we even begin to analyze those situations?
Right, so that's where Kirchhoff's laws come in. And those laws basically provide a systematic way to analyze even those really complex circuits.
Okay, I'm ready for Kirchhoff's laws. What's the first rule all about?
Okay, so the first rule, it's called the junction rule, and it's all about conservation of charge. Basically, it states that the total current that flows into any junction in a circuit
Okay.
has to equal the total current flowing out.
Oh, okay. So it's like traffic at an intersection.
Exactly.
What goes in has to come out. Makes sense.
Yeah, it's a simple but powerful concept.
What about the second rule?
All right, so the second rule is the loop rule, and it's all about the conservation of energy. It says that the sum of the voltage changes around any closed loop in a circuit
Okay.
has to be zero.
Okay. I can definitely see how those two rules would be super useful for figuring out, the unknown currents and voltages in these more complex circuits.
Exactly, yeah.
It would be really helpful to see a specific example to kind of see those rules in action.
Absolutely. We can definitely dive into some examples in part 2 of this deep dive.
Awesome. I'm looking forward to it.
For now, just keep in mind that those two laws, they're powerful tools. They let us figure out those complex circuits by applying those basic principles of conservation.
Okay. I'm definitely going to keep that in mind.
Great.
So join us for part 2, where we're going to put those laws to the test, and we'll see how all this theory actually plays out in some real-world circuits.
So those conservation laws are pretty amazing, right?
Yeah. It's like those basic principles are underlying everything.
They are. And speaking of uncovering those layers, let's dig a bit deeper into this whole concept of resistance.
Okay.
We've talked about how it depends on the material and the dimensions of the conductor, but what's actually happening at the atomic level?
Yeah. The textbook was hinting at something about those collisions that electrons experience as they're, drifting through the conductor.
You're right on the money. Those electrons, they don't just zip through effortlessly.
Oh,
They're constantly bumping into the atoms
I see.
that make up the material. Yeah, and those collisions, that's what causes the resistance.
Oh. So the more they're bumping around, the higher the resistance.
You got to imagine you're trying to, walk through a crowded room, right?
Yeah.
The more people you bump into, the harder it is to move forward.
Right. So it's like that for the electrons, those collisions are slowing them down.
Exactly.
Yeah.
And that's what leads to higher resistance.
Okay, that makes sense. But what affects how often those collisions happen?
Well, temperature is a big one, like we talked about earlier.
Okay.
Higher temperatures mean those atoms are vibrating more energetically.
Right.
So there are more collisions.
So it's like that crowded room gets even more chaotic, making it harder for the electrons to get through.
Perfect. You're getting it. And the type of material matters, too.
Oh, of course.
Different materials have different atomic structures and arrangements, which affect how easy it is for those electrons to move.
So materials where the atoms are really tightly packed together,
Yeah,
that would have higher resistance.
exactly, compared to something with a more open structure.
Makes sense. That's why, some materials are great conductors, like copper or silver,
Oh, yeah, those are the classics.
and others are good insulators, like rubber or glass. It's
Yeah.
all about how their atoms are arranged.
It all comes down to that atomic structure. Yep,
Wow. It's amazing how something so tiny can have such a big impact.
it really is. Now, the textbook mentions something called relaxation time.
Right, I saw that.
It's the average time between collisions for an electron.
Okay. How does that fit into all of this?
So relaxation time, it's a key factor in determining the drift velocity,
Right.
which is directly linked to current.
Okay.
A longer relaxation time means the electrons can accelerate for a longer time between those bumps,
Oh, okay.
resulting in a higher drift velocity.
So materials with a longer relaxation time generally have lower resistance.
Bingo. You got it.
Okay.
And remember, resistance is kind of the flip side of conductivity, right?
Yeah.
A material with high conductivity, that means those charges can flow easily, so the electrons, they have fewer collisions and a longer relaxation time.
It's so cool how all of this connects. Collisions, relaxation time, drift velocity, conductivity, resistance. It's like we're peeking into the microscopic world of electricity.
We are. It's
Yeah.
amazing how it all works together. And this understanding, it helps us see how complex those seemingly simple electrical phenomena really are.
Absolutely. Now let's shift gears for a second and talk about how electric current generates heat.
All right, sounds good.
So we talked about how nichrome wire is used in those heating elements, like in a toaster,
Yeah, good example.
because its resistance stays pretty constant even when it's hot. But what's actually happening there? How is electrical energy being converted into heat?
You know those collisions we were talking about?
Yeah.
That's the key. When electrons collide with atoms in a conductor, they transfer some of their kinetic energy,
Okay.
causing those atoms to vibrate more.
Oh, so it's like a microscopic game of billiards. The electrons are the cue ball, and they're hitting those stationary billiard balls, which are the atoms.
Ha, I love that analogy.
And that increased vibration, that's what we feel as heat.
Exactly.
So more collisions equals more energy transferred, which equals a hotter conductor.
Precisely. It's all a direct result of the resistance the material puts up against that flow of electrons.
Makes sense. This principle is used in so many things. Our electric stoves, even those old-fashioned incandescent light bulbs.
Yeah, those are a classic example.
Speaking of which, I've always wondered how those actually produce light.
Oh yeah, those were pretty clever inventions. So in an incandescent bulb, the filament, which is usually made of tungsten, it gets so hot from the current flowing through it that it starts to glow.
Wow. So it's not just about the heat. It actually have to get hot enough to emit visible light.
Exactly. It's a perfect example of how electrical energy can be transformed into both heat and light, all thanks to resistance.
Okay. That's really cool. Now, remember when we talked about power transmission and how using high voltages helps minimize power loss?
Yeah, all right.
How do they actually get those high voltages for efficient transmission?
That's where transformers come in. They're like the unsung heroes of power grids,
Okay.
and they allow us to increase or decrease those voltages as needed.
Oh. So they're like electrical gear shifters,
Huh. That's a great way to think about it.
adjusting the voltage up or down depending on whether we're talking about, long distance transmission or powering our homes.
You got it. And those transformers, they work based on something called electromagnetic induction,
Oh, interesting.
which we should totally do another deep dive on that topic sometime.
Okay. Add it to the list.
But for now, just know that transformers are essential for making sure that power gets transferred efficiently. They balance that voltage and current.
Okay. I'm adding electromagnetic induction to the list of future deep dives. It's amazing how all these ideas we've talked about, resistance, heat, light, transformers, they all come together.
It really is. It shows how interconnected everything is in the physical world.
And as we continue to explore this whole idea of electric current, I'm sure we'll find even more examples of this. Like you said, it's really elegant.
It really is. And beautiful. You know, those laws that govern our universe are truly something special.
Okay. I'm excited to see where this all goes. Now, remember in part 1, we were talking about Kirchhoff's laws.
Oh, yeah. Our tools for analyzing those complex circuits.
Exactly. You mentioned that you had some examples to help us see how they work in practice.
I do. Are you ready to tackle some circuit analysis?
Let's do it. I'm all charged up and ready to go. Okay, let's put these Kirchhoff's laws to the test. I know the textbook has a few examples, but which one do you think would be best to, really break down?
Well, what about the one with that cubical network of resistors?
Oh, yeah.
I think that's a really good one because it shows us how we can use symmetry to make what looks like a super complicated circuit a little easier to handle.
Yeah. I remember looking at that one and being like, whoa, this is a lot. Resistors all over the edges of a cube. How do we even start with Kirchhoff's laws on something like that?
Well, the key is to see that the cube has a ton of symmetry.
Right.
And because of that symmetry, the current will kind of distribute itself evenly across certain paths.
Okay.
And that means we can simplify things a bit. We can combine those resistors with equal currents, so the analysis isn't quite so overwhelming.
So we're basically taking this tangled mess of resistors
Yeah,
and turning it into a simpler circuit that's like equivalent.
exactly. And once we have that simpler circuit, using Kirchhoff's laws to solve for those unknown currents becomes way easier.
It's like sometimes the scariest looking problems have these really elegant solutions.
That's a great way to put it.
Now, we've talked about batteries as the sources of electric current, but how do they actually work on like a chemical level?
Well, the textbook gives us a pretty good explanation of electrochemical cells, and it all boils down to the chemical reactions happening where the electrodes meet the electrolyte solution.
Okay.
And those reactions involve electrons moving around, which creates the difference in electrical potential between the electrodes.
So the battery is basically transforming chemical energy into electrical energy.
That's exactly it. And, different batteries use different types of chemical reactions. Each one has its own pluses and minuses when it comes to things like voltage, how much charge they can hold, and how long they last.
It's amazing that we figured out how to harness these chemical reactions to make these portable power sources. It's really incredible. But let's go back to circuits for a minute. We've covered Kirchhoff's laws, but I gotta say, putting them into practice is still a bit intimidating.
I totally get that. Circuit analysis can seem really overwhelming when you're first starting out, but trust me, with a bit of practice, it starts to feel much more intuitive. Remember, Kirchhoff's laws, they're just tools.
Right.
They're a way to systematically apply those fundamental principles we've been talking about, conservation of charge and energy.
Okay, yeah. So the junction rule makes sure that all the current flowing into a point equals the current flowing out.
Yep.
And the loop rule makes sure that the voltage changes around a loop add up to zero. But how do we actually use those rules to solve a problem?
So you basically apply them strategically to different junctions and loops within the circuit, and that lets you set up equations that you can solve for the unknowns,
Yeah.
the currents and the voltages that you're trying to find. The textbook actually goes through some good examples.
Yeah, and that example with the Wheatstone bridge was really cool. It showed how even a relatively simple circuit can be used to measure resistance really accurately.
It's classic.
It's amazing how something that seems so simple can actually be so important for practical applications.
Absolutely. It just shows how clever scientists and engineers have been in using these principles of electricity to create tools to measure and understand the world.
It makes you wonder what other amazing applications of electric current are still out there waiting to be discovered.
I know, right? The field of electronics is constantly evolving. It's really exciting.
It is. Speaking of the future, what are some of the things you're most excited about in electronics?
Hmm. Well, one area that's really mind-blowing is nanotechnology.
Hmm.
That's all about manipulating matter at the atomic and molecular level.
Yeah.
So imagine designing circuits and devices, but with atomic precision.
Whoa, so we're talking about building circuits atom by atom. What kind of impact could that have?
Oh, it's huge. Think ultra-powerful computers, super energy-efficient devices, medical devices that can interact with our bodies at a cellular level. The possibilities are kind of endless, really limited only by our imagination and our understanding of the laws of physics.
That's incredible. This deep dive has definitely made me think about those laws in a whole new way. I mean, we started with the basic definition of electric current, and now we're talking about nanotechnology and the future.
It's been quite a journey, hasn't it?
It has. It's really amazing how much we've covered. So to everyone listening, keep those minds curious, keep exploring, and keep questioning. There's always more to learn.
Absolutely.
Who knows what incredible breakthroughs are just around the corner? Until next time, deep divers. Keep diving deep.